Today, we'll go over a real-world example of how we used a distributed lock to fix a data inconsistency issue. So let's jump into the problem. So we're using a Google Calendar with callbacks to notify us that something has changed in Google Calendar. So we have two servers running, server A and server B. So server B gets a callback from Google Calendar. Now, Google Calendar does not give any specific information regarding what's changed. So server B has to go back to Google Calendar and check on the event that it cares about. So while that is happening, server A receives a callback as well, and then go ahead and does the same thing. And so server B then realizes that, oh, there's something in that event that needs to change. So I'm going to go ahead and tell Google Calendar update the event. And then server A does the same thing. So both servers are updating the same event, which could lead to, event duplication, inconsistency in the database, and race condition deadlocks, all kinds of bad stuff. So how are we going to solve this? So we're going to solve this using a distributed lock, which is basically a mechanism that allows multiple servers to coordinate together access to a shared resource, Google Calendar here, and specifically a specific event in Google Calendar being that shared resource. So we're going to be using a Redis to coordinate this sharing. Redis is a in-memory data structure that basically can be used as many things, including database, cache, message broker. And in our case, we're going to be using the set command, set key value with nx, which only will set a key that does not exist, and then a px, which sets a expiration date. So here's the actual code. So we're using Go, and we hook up to Redis, and then we send this command to Redis. Set key value nxpx expire. And then to release the lock, we're going to use the delete command to delete that key, but we're not just going to use delete by itself. We're going to first check whether the value that we're passing in matches what Redis has, right? So this is the recommended flow, which is there in Redis documentation, right? So that way, if a lock times out and a server loses the lock, it can't go ahead and try and release someone else's lock that someone else has, right? So it's kind of a safety mechanism to use this, to do this check. All right, so what does that all end looking like? So here's the solution. So server B gets the callback. It calls Redis to acquire the lock, and then goes and fetches the event from Google Calendar. Then server A gets a callback. It goes to Redis to acquire the lock. Oh, and it does not get the lock, and this is a bug. It does not get the lock. Instead, what it does is it says, okay, I have an event I want to process. I did not get the lock for that event, so I'm going to add it to a queue. So another thing that we added here to this system is a queue. Now, in our case, the queue is a very simple queue. It's a size 1. So it could be basically implemented as a set or as a key. I'm just calling it as a queue in a generic sense, but it's basically a queue of size 1. So it adds that event to the queue. Meanwhile, server B continues, it updates the event, then it releases the lock. Then what we do is server B then checks the queue, right? It's checking if something was added to the queue while it was processing the event. It sees that, yes, there is something in the queue. So then goes ahead and starts up a worker if one is not already started to process that queue. And this works generally pretty well, and we can stop here, but we've actually ran into another problem because we had a priority job that needed to process the event. And in this situation, if there's a lot of callbacks coming in, you can imagine that this queue is always full and someone's always trying to grab the lock, right? So there's an issue. If someone else is trying to grab a lock, maybe it'll get stuck waiting for a very long time, an unacceptable amount of time before it can get a lock. So we needed to add some fairness or some priority so that another process could grab the lock that it needed. So we added a fairness mechanism. And let's see how it looks like. All right, so we have the cron job, right? That's the one that's gonna need to acquire the lock. So let's jump into, like, suppose we have a worker running that's acquiring the lock. And then our cron job that really needs the lock starts up. It tries to acquire the lock and it cannot. So then what did it do? It reserves the lock. So we're using another data structure. It could be a queue. It could just be a key. In this case, we're using a key because we only have a single priority process that needs to reserve the lock. So it says the key saying, no one can grab the lock because I want it. And then what happens is eventually the worker releases the lock. It checks the queue. It says, oh, there's something else. I need to acquire the lock again. But it cannot acquire the lock because the lock was reserved. And this is custom logic, right? Obviously, it has to check whether the lock is reserved before it can acquire it. So it does not acquire the lock. And then the cron job goes ahead and acquires the lock. And then cron job completes while this worker continues looping around and trying to acquire the lock. All right, that's it for today.